To this problem here, it says you have a 45-gram bug is hovering, that's a huge bug, is hovering in the air, and then a gust of wind exerts a force F, which is 4 times 10 to the minus 2 I hat minus 6 times 10 to the minus 2 J hat, and of course the force is in newtons. And then it says how much work is done by the wind as the bug undergoes a displacement delta r of from 2 I hat minus 2 j hat. All right, 2 I hat minus 2 j hat. That's the displacement. So, for example, here's the bug. Here is x, here is y, and then here is the origin. The bug is here, let's say. And then it goes to 2 I hat minus 2 j hat. So let me draw my x-axis here, this way. This is x. This is y. So I have 1, 2, 1, 2, and then minus 1 and minus 2. So the bug was originally here, and then at the end it's at 2 I hat minus 2 j hat. So 2 along the x and minus 2 along the y. So this is the displacement of the bug. Delta r. How about the force? In what direction is the force? The force is in this I hat and j hat direction. So they make an angle with each other. So we don't really have to worry about that. What we have to say for part A, we just use the definition of work. The work done, this is a constant force along a line. And so you get, it is the force dotted with delta r. And so how do you dot two vectors? You have the first vector dotted with the second vector, so it will equal to the x component of the first vector times the x component of the second vector. So it's this x component times this x component. So it will equal to this. And then plus. Alright? What's the x component of the force? It's 4 times 10 to the minus 2. The x component of r is 2. The y component of the force is negative 6 times 10 to the minus 2. And then the y component of r is negative 2. Negative 2. And what do we get here? 8 times 10 to the minus 2 plus, right? Minus 2 times minus 2 is plus. I'm sorry, minus 2 times minus 6 is plus 12 times 10 to the minus 2. So 12 times 10 to the minus 2. And so this gives me 12 plus 8 is 20. 20 times 10 to the minus 2. So that's 2 times 10 to the minus 1 joules of work. Or 0.2 joules. 0.2 joules of work have been done. Now it says, what is the bug's speed at the end of the displacement? Assume F is the only force acting on the bug. We know, well, we use the work energy theorem. The bug is just hovering, so its initial speed is 0. And so the change in kinetic energy, we know that the change in kinetic energy, meaning the kinetic energy at the end minus the kinetic energy at the beginning, will equal to the work done. The kinetic energy at the beginning, the bug is just hovering, so that's a 0. The kinetic energy at the end is 1/2 the mass times the speed at the end squared equals, technically it's minus 0, but this part is gone, equals to W. And W is 2 times 10 to the minus 1. So let's see what we get. So we have 1/2. What's the mass of the bug again? 45 grams. That's 45 times 10 to the minus 3. Or, let's try it. 45 times 10 to the minus 3. Change it to kilograms. Times V squared is equal to 2 times 10 to the minus 1. And so we get V equals to, well, we have to use the calculator here. That'll be 0.45 times 10 to the minus 1. And so we will have 4 over 0.45. Yeah, well, square root. To the 0.1. I got about 2.98. Let me just double check my work. I get, yeah, that is true. So 3, about 2.98 meters per second, approximately 3. That would be the speed of the bug, 3 meters per second. I wonder what bug is it? Because like 10 bugs equal to a pound. A pound is 450 grams approximately. Yeah, I don't know. It's a pretty heavy one. Okay. Let's go to the next one here. Use my pens. They say a 2 kilogram particle is moving along the x-axis, experiences a force, or experiences the force shown in the figure. So it's experiencing this force. And then it says, what's the velocity at x equal to 2 meters? And what's the velocity when x is equal to 4 meters? Well, we know, again, I mean, they're asking about velocity, give me force as a function of distance, of position. I can, it's the, you know that the integral, the work done is the force dot dx. So I know that the work is the integral of f dx from x initial, from x1 to x2. But here's the force as a function of x. The integral is just the area under the curve. So if I go from x equal to 0 to 2, so when, let me come here, when x equals to 2, I would have that the work done will equal to the integral from 0 to 2 of f dx. Integral from 0 to 2. X initial is 0, and x final is 2. Well, how much work have we done? Let's see. How much work have we done? Well, it's the area. It's this. It's this area. And what is that area? It's a triangle. So it's half the base times the height. So half the base is 1 times the height is 10. So you get 10. So it's equal to 10. So 10 joules of work have been done. And I think I'm missing something. I should have written the initial velocity, because to figure out what the velocity is at the end, I need to know what it was at the beginning. So let me check what the velocity was. Yes, the velocity initially is 4 meters per second. Let's see here. If we should add here v initial, v at time t equal to 0 is 4 meters per second. 4 meters per second. Okay. So what's the velocity at, when x is equal to 2? Well, we use the work energy theorem again. The kinetic energy at the end minus the kinetic energy at the beginning is equal to the work done. The kinetic energy at the end is 1/2 m v2 squared minus the kinetic energy at the beginning, that's 1/2 m v1 squared equals to the work done. The work done is 10 for this part. So multiply both sides by 2 and divide by the mass, and you get v2 squared minus v1 squared is equal to 2 times 10 divided by the mass. And so v2 will equal to, move this to the other side, v2 squared will equal to v1 squared plus 2 times 10 divided by the mass under the square root. And V1 is 4, so 4 squared plus 2 times 10 divided by the mass. The mass is 2 kilograms, they said. And so you get, what, 16 plus 10, 26. So that's the square root of 26. It's approximately 5 meters per second. So at t equal to, I'm sorry, at x equal to 2, the velocity would be 5 meters per second. That's what it would be. Now when x equal to 4, well, the work done will equal to the integral from 0 to 4 of f dx. Well, what is the work done from 0 to 4? You've got two triangles. One of them is above and one of them is below. So this triangle here has an area of, we said 10. But what's the area of this triangle? Well, it's half the base times the height. Half the base is 2, right? This is from 2 to 4, so the base is 2 wide. Well, then the height is negative 10. So the area here is negative 10. It's actually negative 10. Whereas this one, it was positive 10. So what's the total work? Well, you did positive work here and then negative work there. So they add up to, in this case, they add up to 0. So they add up to 0. So the work done is 0. If you don't do work, it means the kinetic energy doesn't change. Because the kinetic energy, K2 minus K1, is equal to the work done, but that's equal to 0. That means the kinetic energy at the end will equal to the kinetic energy at the beginning. Well, the kinetic energy at the end is 1/2 mv2 squared, and the kinetic energy at the beginning is 1/2 mv1 squared. Therefore, if we equate these, we get 1/2 mv2 squared equals to 1/2 mv1 squared. Mass is the same, so 2 cancels. So v2 will equal to v1. The speed is the same. My 2 wasn't so good. Okay. And so we get that. All right. I hope these are becoming more clear. Again, ask me during class so it's more interactive and I can slow down, speed up, so we can adjust the speed that way. All right. Let me check the solution, make sure it's correct. Make sure I'm correct. Let's see here. Yeah, in the solution, let me make a mark here. In the solution, what they did is they actually found the equation of this line and then integrated it explicitly. Sure, you can do that, but you don't have to, because this is a line, so the areas are triangles and they're easy to compute. So what they did was this, and there was a typo here. Let me bring it closer. There was a typo here. It should be 4 squared. I'm sorry, yeah, 4 squared. And so you get the square root of 26, which is 5. Square root of 26 is not exactly 5, approximately 5. Yeah, that's the typo there. Okay, so let us go to the next question. Okay, so we have Justin here, a person named Justin. His mass is 30 kilograms. Is going down an 8-meter high water slide. He starts at rest and his speed at the bottom is 11 meters per second. And then it says how much thermal energy is created by friction during his descent. Okay, so let's draw something that resembles a slide. So the slide looks maybe something like that. Right. Justin is here, and then he's here. The kinetic energy here is equal to 0. Let's call it K1. The kinetic energy here is 1/2 mv2 squared. We will calculate it, but I know that here it's 0 because he's at rest. Okay, so what's his total energy at the beginning compared to his total energy at the end, and that's the discrepancy between them would be the work done by the non-conservative force, which is how much heat was lost to thermal energy. Remember, the total mechanical energy is the kinetic energy plus the potential energy, as I discussed earlier. The potential energy here is the gravitational potential energy. And so Justin was at a height initially 8 meters. So his energy at the beginning, his total energy at the beginning, let me call it 1, E1, will be K1 plus U1, but the kinetic energy at the beginning is 0 because he's not moving, so that's a 0, plus his potential energy. Remember, gravitational potential energy is the mass times gravity times the height, mgy or mgh, if you remember it from previous video or a previous class that you took this. So it's equal to the mass times gravity times the height, mgh or mgy. So let's calculate it. So I get E1 will be, Justin's mass is 30, gravity is 9.8, and the height is 8. So let's use the calculator. Use our calculator to get that. So we get 30 times 9.8 times 8. So that's 2352. 2352 joules. That's how much his total mechanical energy at the beginning was. Let's get his mechanical energy at the end. So now Justin is here. So his mechanical energy at the end is K2 plus U2. But then at the end, when he's at 0 height, his gravitational potential energy relative to the ground is 0. So that's a 0. So K2 is 1/2 mv2 squared. So we get 1/2. His mass is 30 kilograms. What's his speed when he's at the bottom? They say 11. So 11 squared. You do this. So you get 11 squared, that's 121, times half of 30, which is 15. So that's 1,815 joules. Okay. So the energy at the end is less than the beginning. How much energy was lost? It's the energy at the end minus the energy at the beginning. And so that gives 1815 minus 2352, and so he lost 2352 to friction. That's 537 joules of energy lost, minus sign. Where did it go? Well, it went into heating the environment or the slide. It goes into heat. If you go to the mechanical energy, we say in this case, is not conserved. However, the total energy, if you include every form of energy, then it is conserved. So if you go to the track here and you look at the molecules, you measure with a thermometer, the track is actually hotter. And what is heat energy, or what is this temperature that has increased? If you microscopically look, you would see that these molecules are actually moving faster. And so they have more kinetic energy, the molecules themselves, microscopically. You would cover that in physics 230. For now, we just say it's lost as heat. So mechanical energy is not conserved. We say that with the understanding that mechanical energy includes only kinetic and potential. It doesn't include heat energy. Okay. We will go to the next problem here. Actually, let me just check that I have it correct. So 537, they have 540. Yeah, that's fine. They rounded. Let's go to the next problem here. Let's go to the next problem. Let me see how much time I have in the video. I will have really short time. So let me stop this video and then we come back to the same problem in the next video. All right.